Bismillahirrahmanirrahim. Today we will discuss about a new kind of diode which is coming under the special purpose diodes. So we will discuss about some special purpose diodes. Okay. Out of this, there are a lot of special purpose diodes are there. Like one of them is Zener diode. Okay, Zener diode. Then another is the light emitting diodes. Then one is the photo diode. Okay, then you can say that varactor diode. Okay, varactor diode. Then one is the tunnel diode. Then Schottky diode, etc. So these are all the different types of special purpose diodes. So out of this, today inshallah we will discuss about the Zener diode. Okay, so we are going to discuss about Zener diode. Okay, it is a special purpose diode. So it is again a PN junction. A diode is a PN junction. Yes, you know that a diode is a PN junction. It is a PN junction, but and it is designed to operate in reverse bias. Okay, this is designed to operate in reverse bias. Okay, in reverse bias. So you have seen the standard diode has been operating normally in the forward bias and forward bias, but this diode is usually used to operate in reverse bias. Okay, reverse bias. And it is a special purpose diode, and it is having a special kind of characteristics. And first, before that, I will show you the notation. The standard diode is usually represented by the symbol like this, right? This is the standard diode, but the Zener diode is usually represented by using the symbol like this. Okay, so this is the symbol for Zener diode. Okay, Zener diode. And the characteristics of the Zener diode, it is almost the same like your standard diode in the forward bias region. It is same like in the forward bias region. So in the case of silicon diode, you know, at 0.7 you will be having a current, and before that, if the input voltage is less than 0.7, there is no current, you can say, and after 0.7 the diode will start conducting. So this is the characteristics in the forward bias. Okay, that means this is the forward voltage and this is the forward current. So you will be getting a characteristic like this. So this 0.7 volt. Now anyway, I have already told you that the Zener diode is normally we will be using in reverse bias region. So in the reverse bias, as you know, there is no current when you give some voltage, but at some point you can see that the breakdown happens. We will call this phenomenon as breakdown, and the voltage at which the breakdown happens, we will call it as the Zener voltage. Okay, and this is the reverse bias voltage. After that, the current will be increasing drastically. Okay, so there is a increase in current. Okay, like in a forward bias, you can say that the current is increasing here also. The same kind of thing you can see in a reverse bias, however at some voltage Vz. Okay, inshallah we will discuss about this in detail. So The Zener diode is also like the normal diode. You can say this is a standard diode with P and N type of semiconductor. Now in the standard diode also, if you can see the same kind of phenomenon. Whenever you increase the voltage, the forward voltage, the forward current will increase, and you will be getting the characteristics like this. This is 0.7. Now at reverse bias, even though if you give very large voltage, you cannot see any breakdown, but if the voltage become very high, this is very high voltage, very high reverse bias voltage, okay, you can see there is a breakdown. This phenomenon we will call it as breakdown, okay, and it is happening at high voltage, usually in a standard diode. So this is the case of a standard diode, okay. So in the case of standard diode, the breakdown will happen at high voltages normally, okay. Actually it is depending upon the doping concentration and all, okay. So this is the case of a standard diode, okay, but maybe at high voltages, okay. But in a so this is the case of reverse bias. But in case of the Zener diode, in the case of Zener diode, we are designed the Zener diode to operate in reverse bias region. So this forward voltage and forward current, and this is the reverse voltage, that means reverse bias. You can say that you have the breakdown in Zener diode also, but you can control this voltage. You can control this breakdown voltage, okay. That means the breakdown voltage will be controlled to some particular voltage, so that you can have breakdown in almost at any level, you can say. For example, the breakdown, you can have a breakdown at 5 volt, 6 volt, that is reverse voltage, 5 volt, 6 volts, 2 volt, 3 volt, etc. Okay, so this problem, how it was solved? It was solved by changing the doping concentration, okay, changing the doping concentration. So in Zener diode, you know that we have a p-type semiconductor and an n-type semiconductor. Here for getting p-type, we usually add the group 5 elements, sorry, group 3 elements, and for getting the n-type, we usually used to add the group 5 elements, okay. So we will add more, we can say we will add more in the case of Zener diode, okay. The doping concentration is pretty high in order to achieve this task. So whenever the doping concentration become very high, you can say that the depletion region in the Zener diode, this is the depletion region that we have already discussed while discussing the diodes. So the depletion region, that is the region with ions, the depletion region become, we can say that the depletion region in Zener diode is very thin, okay, very thin. So when you apply the reverse bias voltage, and you can see that the doping concentration, I will write this one also, the doping concentration is very high in Zener diodes, okay. And because of this doping concentration, because of the very high doping concentration, the intensity of the electric field, which is created due to the reverse bias, will be very strong, so that it may pull out the electrons from the valence band, and it will cause a very large current, okay. It is because of the very high doping concentration. And this phenomenon will also happens in the standard diode also. This will happen in standard diode also, but it will happen at high voltage. Okay, it will happen at high voltage. In high voltage, the electron will be coming out of the bond. You can say this is a lot of electrons will be there. The electrons will be coming out of the bond. It will be hitting on the electron sitting in the other atom, and it will drive out the electron in the other atom, and it will cause the increase in the number of electron, and this electron will hit on the other atoms, and it will create another two, and it will be like an avalanche. Okay, so it will be like an avalanche. That's why we usually call it as avalanche breakdown. Okay, in the case of the standard diode. But in Zener diode, we will call this phenomenon as the Zener breakdown. We will call this phenomenon as Zener breakdown. What is the Zener breakdown? Because of the Zener breakdown, you will have a current during the reverse bias also. Okay, so if you are giving this is the forward voltage and this is the forward current, so you will be having a current in the reverse bias at a voltage Vf. So this is phenomenon is known as Zener breakdown. During this Zener breakdown, you will be having a voltage across the Zener diode which will be constant. Okay, so this is the Zener diode. You can say that this is the N region and this is the P region, and we will be applying here positive and we will be applying here negative. So the current will be going down, that means positive to negative. So the voltage across the Zener diode will be Vz, like your 0.7. So the breakdown which is happening in Zener diode, which is known as the Zener breakdown, and in standard diode it is known as the avalanche breakdown. Why it is so? Usually the avalanche breakdown happens at higher voltages, okay, but the Zener breakdown happens at lower voltages. Okay, how it is possible? By increasing the doping concentration. When you compare the standard diode with the Zener diode, you know that the doping concentration is very high. Okay, it is very high in Zener diode. Okay, by changing the doping concentration, that means if you change the doping concentration, I can say doping concentration. If you change the doping concentration, you can change the Vz. What is Vz? Vz is the voltage at which the breakdown happens. So if you change the doping concentration, okay, if you change the doping, you can change the Vz. But in standard diode, you will be using a fixed doping concentration anyway, according to the application which is suitable, which is required for a particular application. So it is the doping concentration is usually moderate. Okay, now the main point, the standard diode usually work in forward bias. In forward bias, this is the simple for the diode, and in forward bias for a silicon diode you will get the 0.7 as the voltage. So you will give positive supply here and you will give here negative supply. Okay, This is the case of the standard diode. So standard diode usually work in forward bias. That means you have 0.7 volt here. That means you will be applying here positive and you will be applying here negative. Okay, but because this is p-type semiconductor and this is n-type semiconductor, so this is forward bias. But this Zener diode usually works in reverse bias. Suppose you have a Zener diode. This is the symbol for the Zener diode. This is p-type, this is n-type. You will be applying here positive and you will be applying here negative. That means the voltage across the Zener diode, if it is on in reverse bias, okay, that means you are applying reverse bias. It will be Vz. Okay, this you should know. So in Zener diode, the voltage across the Zener diode in reverse bias, and if it is on, if there is a current through the Zener diode, the voltage across the Zener diode will be Vz. Okay, now we will see the details of the characteristics of the Zener diode. So the Zener diode characteristics is something like this. This is the forward voltage, this is the forward current. Okay, now this is the, what do you mean by this forward voltage? Forward voltage means you apply here forward bias. That means this is p-type, this is n-type, this is like this. So this is the current will go from positive to negative. So this is the forward bias. Okay, so in the forward bias you can see the characteristics is like the standard diode. So after 0.7 you will get the current. Okay, so you will have a resistance also. That means delta Vf and delta If. Okay, so the forward resistance of the diode you can say Rd dash. Okay, so 1 by Rd dash is equal to delta If by delta Vf, or Rd dash is equal to delta Vf by delta If. So this is the case in forward bias. Okay, this is the case in forward bias. Anyway, we are not going to focus on the forward bias. Our main area of operation in a Zener diode is the reverse bias. So this is Zener diode characteristics. So in reverse bias you will not have any current because you are applying a reverse voltage. Reverse voltage means you have a Zener diode like this. This is N region, this is P region. To the N you will apply a positive supply and to the P you will apply a negative supply. So the current will be from positive to negative. So the voltage across the Zener diode will be positive, negative, Vz. Okay, it will be something like this. Now you will not get any current until you reach the Zener breakdown voltage. After reaching that, the current will increase drastically like in forward bias. Okay, you can see in forward bias the current is increasing, right? Like this you are getting a high current. Okay, so the minimum current which is required to turn on the Zener diode, we will call this as IZK, or we can call this as the knee current. Okay, knee current. Now if the current exceeds a maximum limit in the Zener diode, what will happen? The Zener diode will get heated and it will burn. Okay, so there is a maximum limit for the Zener diode current also. So that is known as IZM. So this is the maximum current. So this you can say it is the minimum. Okay, minimum to turn on the Zener diode in reverse bias. Okay, and this is the maximum current which is passing through the, which can be accommodated in a Zener diode. If you pass any current above this limit, what will happen? The Zener diode will damage. Okay, so this is the characteristics of the Zener diode. Now you can see this line is this is a straight line, so the voltage at the center, that means we usually call this is the voltage is approximately equal to Vz, okay, and the current we will call this as the Iz. Okay, this is the optimum current, or you can say this is the optimum current, okay, which is the at the center of the operating region. Okay, so the operating region for the Zener diode will be from Izk to, it can go from Izk to Izm. So the operating region, okay, so operating region, the current Iz can go maximum to Izm, and it can go minimum up to Izk. If it go below Izk, this diode become turn off and there is no use. Okay, it become useless. So we can also, since you can see that this curve is having a slope, we can define the slope of this curve. Okay, so this point you can say, I can redefine this. At Iz, the voltage I can say it is Vz. Okay, so you can see that at a maximum limit also the corresponding voltage is there. At a minimum limit also there is a corresponding voltage. So this is, you can say that the maximum it can go, and this is the minimum. However, these maximum and minimum are very close. That means you can say that Vz will be almost constant. Okay, suppose if you have the resistance from this curve, the resistance from this curve, you can say that this is delta Iz and this is delta Vz. Then you can have a resistance of the Zener diode as the resistance of the Zener diode, you can say that Z, which is equal to delta Vz by delta Iz. So what is this? Delta Zz is the resistance of Zener diode. Okay, this is the resistance of the Zener diode. So what is this point? So the maximum voltage, you can say it is nothing but Vz, the magnitude of the voltage I am saying, Vz plus Izm, this is the maximum point. So the difference in the current is nothing but Izm minus Iz into Zz. Okay, and what is the minimum? The minimum point is nothing but this is the Vz you have, so Vz, and it is less than, so minus the difference in the voltage is nothing, difference in the current is nothing but Iz minus Izk. Okay, so this is nothing but the minimum voltage. So let us conclude. The Zener diode has the operating region as shown here. It will work like this, almost this is Vz, and the current, the minimum current is Izk and the maximum current is Izm. The optimum current, or the good operating region, is nothing but Vz and Iz. So the Q point we can say, or the operating point, we can say operating point, or the QZ operating point is Vz and Iz. Okay, so this is IR this is IF and this is IR, reverse current. Okay, this is the reverse voltage. Now that means the current can change from IZ, it can go maximum, or we can say that it can go to minimum of IZK and it can go to the maximum of IZM. Similarly, the voltage VZ, it can go to, this is the minimum and this is the maximum. Okay, the VZ, it can go to the maximum of VZ plus IZM minus IZ. Okay, IZM minus IZ into ZZ, and it can go to a minimum of VZ minus IZ minus IZK into ZZ. Okay, so this you have to remember. Now we will see a problem. This problem 1. Okay, the characteristics of Zener diode is shown below. Okay, obtain the Zener impedance, that means the resistance of the Zener diode. So this is the characteristics. You can say the characteristics is is like this. Okay, now it is given, this is IZK, this is the reverse current. Now this is the voltage, we can say this is VZ. Okay, and you have a maximum limit which is known as IZM, and there is a variation. They have also shown the variation here. That means you have a variation like this. That means you have a delta VZ which is equal to 50 millivolt, and you have a delta IZ which is equal to this is varying from, this is 10 milliampere and this limit is 15 milliampere. So delta IZ is nothing but 15 minus 10 milliampere, which is equal to 5 milliampere. So it is given delta VZ. So the solution, it is given delta VZ is given in the, and it is evident from the graph that it is 50 millivolt. Okay, and delta IZ, it is given, you can say, you can find it as 15 milliampere minus 10 milliampere, which is equal to 5 milliampere. Now the Zener impedance is ZZ, which is equal to delta VZ by delta IZ. Okay, which is nothing but 50 millivolt divided by 5 milliampere, which is equal to 10 ohms. So the resistance corresponding to this is 10 ohms. Okay, that means ZZ is 10 ohms. Okay, so the slope of this curve, you can say the slope is equal to 1 by 10. Okay, slope is equal to 1 by 10. Now we will see another problem. Problem 2. That means that is determine the minimum and maximum input voltages that can be regulated by the Zener diode voltage regulator circuit shown in figure below. Okay, the details regarding the complete design of the voltage regulator we will be seeing in the next class. Anyway, let us do this problem. You can see that for the Zener diode, this is the Zener diode they have used in the circuit. Zener diode, it is given that Vz is equal to 5.1 volt at Iz is equal to 49 milliampere. Okay, so Vz is given, Iz is given, and also it is given Izk. Izk is equal to 1 milliampere. Okay, and it is given Zz equal to 7. Okay, 7 ohms at Iz. Okay, so the solution. So before that, I will give you the picture, the circuit diagram. It is Vz, sorry, not Vz, it is Vin. Vin is changing, and R is given as Zener diode. You can see the Zener diode is in reverse bias now. Okay, and we will be taking the output here. This is the output. Now we want to find what is the maximum Vin we can give and what is the minimum Vin that we can give. Okay, so you know that solution, you know that whatever the voltage you give, the Zener diode should operate in its operating region, right? It should not run away from the operating region. That means Zener diode is having the reverse voltage, reverse current. The current in the Zener diode is Izk is maximum, sorry, minimum, and maximum is Izm. The current in the Zener diode should be between this limit. It should not be less than, the current in the Zener diode should not be less than Izk. This should not happen. And also the current in the Zener diode should not be greater than Izm. This also should not happen. That means the Zener current should be less than Izm and it should be greater than Izk. So this is the condition that we need. Okay, we have to ensure this condition. If you don't ensure this condition, if Iz become less than Izk, your Zener diode become off. If Iz become greater than Izm, your Zener diode will damage. So you don't want both. So what you have to do? So you have to maintain the current. Okay, the resistance is also given, sorry, I forgot to write it. The resistance is given 100 ohm. Okay, so first of all we can I will redraw the circuit first. You have a V in here and R, which is equal to 100 ohm, and this is Zener diode. Okay, and you are going to take the output. Okay, so what is V out? You can see, first of all, I will take the characteristics curve. This is the forward current and this is the reverse current, and this is the characteristics. Okay, and this is Vz. Now you can say that the voltage across the Zener diode was at the center, at the Q point, at the optimum point, it is 5.1 volt, and this current, I think it is given as Iz, which is equal to sorry, Iz equal to 49 milliampere, and Izk is given as 1 milliampere. Okay, and this is IZM. IZM is given. IZM is not given, I think so, right? In the question, it is given that the power dissipation is given. I forgot to write it. The power dissipation, that is the PZ is PD is given. PD maximum is given as 1 watts. So you can calculate IZM because you know that power equal to voltage into current. That means the current is equal to power by voltage. So you can calculate the power as you can calculate the IZM as approximately, which is equal to 1 watts divided by 5.1 volt, which is equal to 196 milliampere. Okay, now you got all the limit. Now you can find this minimum limit. Also you can obtain this maximum limit, as we have told in the previous, just before some 20 minutes, that the maximum and the minimum will follow this rule. That means you can find the minimum voltage which will appear across the Zener diode as Vz minus Iz minus Izk into Zz. Okay, so you will get this as, this is equal to, what is Vz? Vz is 5.1 minus Iz is 49 milliampere minus 1 milliampere into 7 ohms. Okay, you will get it as 4.76 volt. So you will get this point as 4.76 volt. Okay, similarly you can find the maximum. You can obtain the maximum. What is maximum? It is nothing but Vz plus Izm minus Iz into Zz. Okay, this is nothing but Vz. How much it is Vz? Vz is equal to Vz equal to 5.1 plus Izm is 196 milliampere minus 49 milliampere into 7 ohms. This is nothing but 6.13 volt. So I will redraw it. You can say that this is the Zener characteristics. This is the Zener characteristics, and this is the point of 5.1 volt, and at Izk at 5.1 volt the current was given as 49 milliampere, and at Izk the corresponding voltage has been reduced slightly. You can see it is only a very small change. So it is nothing but that we have got it. It is nothing but 4.76. Okay, 4.76 volt. Okay, 4.76 volt, and the maximum that we have got it as 6.13 volt. That means it happens during when the current become Iz maximum, which is 196 milliampere, and this is I think this is 1 milliampere, right? It is 1 milliampere. Okay, yeah, it is 1 milliampere. So this happens at 196 milliampere, then the current and then the voltage is 6.13 volt. Okay, you see here there is a large variation of the current from 1 milliampere to 196 milliampere. The voltage is changing from 4.76 to 6.13. It is a very small change. That means we can regulate the voltage by using the Zener diode. So that's why it is mainly, that's why Zener diode is mainly used in voltage regulator applications. Now I will draw the circuit again. You have, the question is not to find the minimum and the maximum limit for the output. We want to find the minimum and the maximum limit for the input. Okay, so this is our output, V out. Okay, now when the output is minimum, the voltage at the output we have seen it is 4.76 volt, right? So we will first take this when the output is minimum. Okay, when the output is minimum, when output is minimum, you can say that V out is equal to 4.76, and the current through the Zener diode is going like this, right? And this current is IZK only, and this R is equal to 100 ohm. So this will happen, that means the voltage output become minimum when the input become minimum, right? So minimum input, I can say this is the V in minimum, is nothing but, if you write the Kirchhoff law in this loop, you will get it as V in minimum is equal to IZK into R plus V out minimum. Okay, if you write the Kirchhoff law and solve it, you can get it like this, right? So this is nothing but, you will get it as IZK into R. IZK is 1 milliampere into 100 ohm plus this is 4.76 volt. This is nothing but 4.86 volt. So the input, the minimum input that you are getting is 4.86 volt. If you give any input which is less than 4.86, what will happen? Your Zener diode will not get the sufficient current. The current become less than IZK, and it will goes to, and it will turn off. Okay, now we will see another situation. That means this is R equal to 100 ohm. When the output is maximum, you are getting the voltage at the output V out, which is maximum, you are getting it as 6.13 volt, right? Now whenever output is maximum, you can say that input is also maximum. So the maximum input you will get, you can see that this maximum input is dropping across the resistance and across the Zener diode. So maximum input is equal to the current IZK, because during the maximum input the current will be maximum, right? That means the current will be IZM, not IZK, IZM. IZM into R plus V out, which is maximum. What is IZM? IZM is equal to 196 milliampere into 100 plus this is 6.13 100 ohm, and this is 6.13 volt. You will get it as 25.7 volt. So you can say that this is 25.7 volt. So you see here, even though you are giving 25.7 volt, the output is only 6.13 volt. That means if you change the output, that means if you vary the input, the output is not going to change, and you can vary up to 25.7. So what will happen to the remaining voltage? The remaining voltage will be dropped across the resistance. So across this resistance, at this time you can see 25.7 minus 6.13 volt. This will be the voltage across the resistance. That's why we are going to put the resistance. So resistance will manage the voltage and it will limit the current through the Zener diode. Now if you give any voltage, if you give V in greater than this 25.7 volt, what will happen? Your Zener diode will damage. Okay, and in the previous situation, if you give any voltage V in less than your voltage here 4.86 volt, okay, what will happen? Your Zener diode will turn off and you will not get regulation. Okay, so this is the working of the Zener diode. Anyway, inshallah we'll see some more problems in the next class. Okay, thank you.